Your 8-core CPU just silently murdered your program, because 4 of its cores cached the same variable with 4 different values. Every core in a multi-core CPU has its own private L1 cache, a tiny SRAM scratchpad that runs at full core speed. Without a referee, 4 cores can all write x equals 42 to their own L1s, and the rest of the system sees 4 different realities. The memory controller in DDR5 can't fix this. It only sees the final write after the damage is done. Cache coherence is the protocol that keeps every private cache synchronized, so the whole chip sees one consistent memory image. It's not a hardware feature bolted on at the end. It's a distributed state machine running in every cache line, tracking who might have a copy and what they're allowed to do. Cache line states. Each 64-byte cache line in every L1, L2, and L3 slice carries one of 5 MESI states: modified, exclusive, dirty; exclusive, clean and unique; shared, clean and duplicated; invalid, must refetch; or, on some ARM chips, forward. Owner forwards the line to another requester. Bus snooping. Every cache controller taps the on-die ring bus, Intel's Ring or AMD's Infinity Fabric, watching every memory transaction. Instead of polling, the bus uses MESI broadcast, a single RFO, read for ownership. Packet races around the ring at 1 to 2 nanoseconds per hop. Read miss triggers RFO. Core 0 misses address 0x1000. It broadcasts an RFO tag with the address. All other cores snoop the bus. If any core has the line in modified or exclusive state, it stalls its pipeline for 3 to 5 cycles, writes the dirty line back to L3, a snoop push, and downgrades to shared. Dirty data write back. The modified holder, Core 1, pushes 64 bytes through the ring bus at 512 gigabits per second on a 5 GHz chip. The data lands in the L3 slice in 12 to 15 nanoseconds while the requesting core spins in a cache miss stall. State upgrade. After the write back, Core 0's line enters modified state. Every other copy is invalid. If Core 2 later reads the same line, it will snoop the bus, see the invalid, and fetch a fresh copy from L3. Silent evictions. When a core's L1 fills, it evicts an invalid line first. If no invalid exists, it picks the LRU, least recently used, line, checks its state. Shared lines are silently dropped. Modified lines are written back to L2 in 20 to 30 nanoseconds. Directory versus Snoopy. Intel's L3 uses a directory in each slice, a 128-bit vector listing, which cores hold shared copies. When Core 3 issues an RFO, the directory outputs a 128-bit mask in 8 nanoseconds, telling only the sharers to flush, saving power compared to broadcasting every request. Compile a tight loop that increments a shared counter 10 million times on a 16-core Ryzen 9 7950X. Without coherence, the final count could be anywhere from 10 million to 160 million. With coherent caches, the RFO storm pushes dirty lines back and forth at 20 ns per handoff. PerfStat shows 4.2 billion cycles total and a final count of exactly 10 million. Misconception. Cores just wait their turn. Reality. They race. The first modified holder wins ownership. Others stall until the write-back completes, measured in cycles, not fairness. Cache coherence is a real-time distributed protocol where every cache line's MESI state and bus snooping guarantee one global memory image at the cost of 5 to 20 nanosecond stalls every time a line changes hands. Subscribe to Tech with Joel, and I'll break down how something like this actually works every single day, starting tomorrow with the silicon-level trick that makes DDR5 run faster than DDR4. Which cache coherence protocol does your phone use, MESI or MESI? Drop a comment. Subscribe to Tech with Joel.